let's discuss the very first one, big O notation. So what big O notation is? Big O notation indicates maximum time required by an algo for all input value. And we can also say this is the worst time complexity. So as we saw that there could be a scenario in which the particular program takes maximum amount of time. That is denoted by big O notation. So big O notation corresponds to worst case time complexity, or the maximum amount that can be taken by a program for all the inputs. And we have this mathematical representation also, or mathematical definition also for this big O notation. It says, consider function fn the time complexity of an algo and gn the more significant term, and if some constant multiplied with gn is always greater than fn for all n greater than n naught, c greater than 0, and n naught greater than 1, then we can write fn as O of gn. Okay, let me try to explain what is this saying. So let's say let's take an example. We took an example of let's say this is the time complexity. Then fn in this case will be 3n plus 2. This is the fn, and gn in this case will be n, because this is the most significant term. So this is the gn. So what this particular definition is saying, that if there is a situation, so let's say this is fn and this is gn, this is time and this is the number of input, this is the input size, and we are trying to represent it pictorially using a graph. So let's say this is f of n, which in case is 3n plus 2, and this is c into g of n. C is some constant, we will see what's the use, and which will be n in this case. So what it is saying, that after a particular input, after a particular value of n, there might be a situation that this c into g of n will be always greater than f of n. And in case such n naught and such g exist, in case this scenario is possible, we can represent f of n as O of g of n. This will be the worst case time complexity. Let's say we have 3n plus 2 in this case. Our f of n in this case is 3n plus 2, and g of n is just n. So now we need to find a c and an n naught for which c into g of n will be always greater than f of n. So okay, now as we saw that f of n in this case is 3n plus 2 and gn is n. In this case gn is the most significant term and fn is the time complexity. So we want to have, in case we want to write this f of n as O of g of n, in case we want to write this, then in our case, since g of n is n, we want to write time complexity as O of n. Then what do we need? We need some c such that c into n is greater than 3n plus 2. So we want such c and n. So let's say we have c is equal to 1. Okay, no, that won't happen. So after you do such substitution or such trial method, you find that c is equal to 4 and n is greater than 3. So when c is equal to 4 and after n is greater than 3, then c into n will be always greater than 3n plus 2. So if you put this, 4 into n is 3, and this is 3n, which is 3 into 3 plus 2, 9 plus 2, 11. So we see that 12 is greater than 11. Now let's put n is equal to 4. So we have c into n, we have 4 into 4, 16. This will be 3 plus 4, 16 plus 2, 12 plus 2, 14. So we say that 16 is greater than 14. So we can say that when n is greater than 2 and c is equal to 4, c into n will be always greater than 3n plus 2. So this holds true. Hence we can write that, we can represent f of n as O of n. This is about big O time complexity. mostly we will calculate, mostly we would, when you are writing a program, we want the worst case time complexity, that what will be the worst scenario that will happen. So we refer to this O of n only while writing a program. Next is big omega notation. Big omega is just opposite to what is big O notation. In this case, it defines the lower bound, or it defines the minimum time that could be taken by a particular code or algorithm. Or we can say that this deals with the best case complexity. Now, if we again try to define big omega, then we say that if Fn is the time complexity and Gn is the most significant term, then if there exists a C and there exists an N naught, and for that C and N naught, C into G of N, okay, this is nothing, C into G, if C into G of N is always less than F of N, then we can represent F of N as big omega of G of N. Talking about graphically, so there has to be some N naught and there has to be some C, such that after this N naught, after all the values of this N naught, this F of N is always greater than this C into G of N. Let's say we have F of N equal to 3n plus 2. In this case, what is G of N? G of N is the most significant term, which is N here. So what is this? So we need some C such that C into N is always less than 3n plus 2 after a particular value of N. So we want a C and we want an N, so that after a particular value of N and for a particular value of C, this statement holds true. So when we put C equal to 1, and let's try to put N is equal to 1. So we have 1 here and we have 5 here. So we see that this holds true for N is equal to 1 and C is equal to 1. Let's try to put N is equal to 2 and let's C remain as it is. So in that case, it becomes 2, 8. So this holds true for 8 also, for N is equal to 2 also. So we can say that for C is equal to 1 and N greater than equal to 1, 3n plus 2 will be always greater than C of N. So we can represent 3n plus 2 as omega of N. This is omega notation. Okay, now let's try to understand big theta notation. Big theta notation deals with the average time complexity. So what is the average time that will be taken by a program? That is big theta notation, that is represented using big theta notation. Now again, coming to the definition. So big theta notation says that if Fn is the time complexity of an algorithm and Gn is the most significant term, then there must be some C1 and C2 and N naught such that Fn lies between these two, C1 into G of N and C2 into G of N. As you can see that after particular N is equal to N naught, after particular time of after particular number of input, it will happen that Fn will lie in between C2Gn and C1Gn. So in case we are able to find some C1 and C2 and we are able to have some N is equal to N naught such that this following condition holds true, then we can say that F of N, we can represent F of N as theta of G of N. Now let's say this is the time complexity and this is G of N, which is the most significant number, and we want to see if there exists some C1, C2 and N naught such that for this C1, C2 and values greater than equal to N naught, this condition holds true. Sorry, G of N. Or C1 into N greater than equal to. So we want some C1 and C2 and N naught such that this condition holds true. So what happens when we put C1 is equal to 1 and C2 equal to 5 and for values N greater than equal to 1, we have calculated that this condition will hold true. So let's put C1 is equal to 1. Let's put these values basically. So we have N is 1. So we have 1 n is 1, so this is 5, and this is 5. So we see that condition is holding true. Now increasing n to 2, we see that this is 2, this is 8, and this is 10. So again this condition holds true. So we can write 3n plus 2 as theta of O of n. So this is about the asymptotic notations. In asymptotic notation, it's just a way to represent the average case, worst case and best case time complexity. And when you will be writing a program or when we'll be giving an interview, most of the times it may happen that they'll ask you about all the three complexities, and you will get objective questions also around that a particular program, that will be the average case time complexity and what will be the best case time complexity. So, and it may happen that in a particular program coding interview, you're writing a particular code and they will ask you for a worst case time complexity. So let's see that how we can calculate. We saw one example that how we can calculate time complexities. Let's see more examples on how we can calculate time complexities in case of recursive and iterative codes.